Okay, let's talk about the conservation of energy. And let's say if we have a box here. This is a height. Let's say this is a height. Let's call it H. And this is the floor, and this is the height here. And then you have a particle here. Let's say you have a box of mass M. And okay, so we do have gravity pulling down. So remember that all this is inside a gravitational field. And you do have a gravity pulling down. Here is all these arrows represent gravitation, or the force of gravity. Okay, so we know that the work energy theorem is delta kinetic energy, and this is the theorem of kinetic energy. Work is equal to the kinetic energy. But also, like in this case, we do have here a force going this way, which is mg, and that would be a gravitational force. And the displacement to take this, to move this particle was from the point A to the point B. The point B is over here, point B. So we do have here that the work done, in this case, the work done is going to be the work done by the gravitational force, and the gravitational force is a vector. Dot product with the displacement vector, and the displacement is a vector too. So we have to solve this one right here. And the work done is going to be mg, because that's the force of gravity, times delta y, and times the cosine of 180 degrees, because we have here that the displacement is this one right here. This would be delta y, and the gravity is pulling down, it's pulling this way. So this would be mg right here, and the angle between these two guys is 180 degrees. So the work is going to be equal to a minus delta u, and this would be the work done by the force of gravity. And we can say over here that the work is equal to minus delta u. So the work is equal to delta ke, which is the work is equal to the increase in kinetic energy. So this one is the increase in kinetic energy, and this one is the increase in potential energy. So U stands for potential energy. Potential energy, okay. And KE stands for kinetic energy. Kinetic energy. Let's write this one a little better. Kinetic energy here. Okay. Kinetic energy. And as we can see, the work is delta kinetic energy, which is the increase in kinetic energy, and the work is also the negative increase in potential energy. So we can equate these two guys. So we can say that minus delta U is equal to the work, but the work is also the delta kinetic energy. So we have here that we can send this guy to the other side. Let's do that. So we have that minus delta U is equal to delta kinetic energy, and then we send this guy over here. So we have 0 is equal to increase in kinetic energy plus increase in potential energy. And we have this little nice equation for the conservation of energy. So we have that 0 is equal to 1/2 of the mass final velocity to the square minus 1/2 of the mass initial velocity to the square plus this delta U, which is final potential energy minus initial potential energy. And we can send some of these guys to the other side of the equation. Let's send the negative guys. So 1/2 of the mass initial velocity to the square. We're going to send this guy to the other side. And this one too, we're going to send him to the other side over here. So it's going to be plus the potential energy. Okay, let's erase this one right here, the potential energy right there. So, and that's going to be equal to 1/2 of the mass final velocity to the square minus plus potential energy final. So we have here that this here is the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And this is the we can say that this is the initial energy, and that's equal to the final energy. And as you can see in the equation, the energies are the same, which tells you that there has been conservation of energy in this case. And that's how you get the equation for the conservation of energy. So we have kinetic energy plus potential energy before and after. They stay the same. Thank you. And we'll do some problems using this idea. Bye.